They earn their spots.
Jeff, you know it's,
I mean, they're
Yes, I know, but I've got to for their name.
Good morning, folks. Tomorrow, well, originally over the weekend, I was going to have you tomorrow do an activity outside. That's going to be changed to Thursday. But I'm still going to give you the lesson you need today to do the activity tomorrow, or Thursday. I'm not going to be here on tomorrow or Wednesday. UNM invited me to go to work with them on some collaborative things. Oh, and by the way, I'll pitch this as a commercial. Anybody interested in getting college credit for C+ computer programming? Hey! We're setting up the deal right now. Jeff's not supposed to be in this space at this moment, but he heard the commercial. Tomorrow and Wednesday, I'm working on that deal for C+ computer programming. You get college credit at UNM, as well as high school credit here at the Academy for that particular opportunity. We hope to have that ready to go next year.
Well, I'm on board.
Okay. We're going to, today though, I'm going to talk about piecewise functions.
So for now, I have to do this math.
Yeah.
I'm going to Miami for my cousin's bar mitzvah, so I'll be out this Thursday and Monday.
I'm sure the YouTube world is very anxiously excited about sharing it. We are going to talk about piecewise functions. This is what we're going to use in an activity that we are going to title Moving Me. Not despicable, but moving. So we're going to do piecewise functions. Really what a piecewise function is, we're going to put, in this section, we're going to put a bunch of linear things together. So in your books, I'm going to have you turn to page 130. If you're in the YouTube world, it does start there. There's an activity that communicates to you piecewise functions on page 130. What a piecewise function is simply taking a number of different functions and piecing them together. So just as a quick sketch on a vertical horizontal axis, what a piecewise function, Cheyenne, can look like is, in graphic form, is a line like that starts and then stops. It's sort of like a line segment. Remember studying that in geometry? So instead of arrowheads being on either end of it, we're just going to stop it right there. As a matter of fact, part of the vocabulary I can communicate that if I'm going to call this the, let's call it the f function. If that's the f function that starts and stops where you see it, what would the domain of that function be? What's the domain of f? 0?
Would it be 0?
We just learned last week what domain, in mathematics, how we identify and define domain.
Domain is x.
Where are all the x coordinates, right? So again, for this piece of the f function, I'm saying it starts and stops there. What's the domain as it's identified there in that graph? As you see the axis labeled. What is the domain? Where does it start?
Oh, it starts at 0.
And where does it stop?
And it stops at
Starts where?
0.
Yeah, so that domain for that particular function would be from 0 to 10. And any numbers in between. Okay? That's the domain. Now, I probably should communicate that and write it in this language. So you can read it in inequality. As a matter of fact, we should probably use these symbols equal to, since we're going to include those points. You see what I'm saying? What's the range? No, you won't know what the range is. Let's say I label that as 20. What's the range now? Yes?
Why did you put 0 is less than or equal to x?
Well, I didn't. I actually wrote x is bigger than or equal to 0 or less than or equal to 10. So x is in between 0 and 10. The domain. The domain's in between 0 and 10. See how the x is written in between 0 and 10? Same kind of way. All right, good question, Sarah. So that's the domain. That's one of the functions that we can write. But what if we added another linear graph? And again, I'm just sketching this. This isn't to scale. But what if I did that? And this, again, we will communicate as another function. I'm going to give it another name so you're not confusing the two. I'm going to call it the g function. G. But it's another function that I've pieced to the f function. So now we have pieced two functions together, two linear functions, or is it linear? Is it linear? Are they linear? Well, why? How do you know?
Because the x is squared.
The vertical line test
Well,
also.
we haven't seen any algebra.
Well, nothing's squared.
We know it's a function, but how do you know it's a linear function?
It makes a line.
It's a straight line, right? If all I'm talking about is this g function, it's pretty straight. Now, it can go on infinitely, but we're just going to use that part of the g function. We're going to start it where?
At 10,
And where are we stopping it?
20,
What's the domain?
10, 20.
10 to 20.
Well, then
So in this
x is
case,
greater than or equal to-
Yeah, so the domain, as you're capturing it in your notes, of the g function is between 10 and 20. Agreed? As it's labeled? What about the range? What about the range of the g function?
It would still be same as the f function of 0 to 20.
Yeah, let's say that. Let's write the range of the f function. We didn't write it down. But what is the range?
It goes up to 20, so it would be 20.
Again, it starts at 0, and range we usually call y, right? And it goes out to 20. That was the range of the f function. It starts at 0, ends at 20. All things in between 0 and 20. Does that make sense?
Oh, that's the range of the.
Is that the range of g?
No.
Where does the
The range
g
of g is
function?
20.
Ah, the range of the g function, as we've identified, is nothing ever anything but what?
20.
That's all it can be. It's only that height. It never goes up any higher than that, right?
Okay.
Y is equal to 20. That's the range of the g function. It's flat, okay? This is similar, by the way, to the data that we're going to collect tomorrow or Thursday in our moving me exercise. So really what that has is that, and that's an example of the geometry of a piecewise function. Let's write it. Let's write the algebra for it. Okay? So that's the geometry of it. That's the graph of it. Let's write the algebra of this piecewise function. Since it's two functions that have been pieced together, you're going to have to come up with two algebra statements we call functions. Let's write the algebra for the f function. Since it is linear, you said, from here to here, it's a straight line, right? What's the algebra got to look like? The exponents on the variables have to be what? Or 0, right? 1 or 0. So we have a slope times that value plus b, right? It's got to be linear, right? That we've been working on since August. Well, what is the slope?
2.
Is it? For
Is
this?
it 2?
20 divided by 10 is 2.
All right, so Jacob is saying it's the change in the y, change in rise, divided by the change in the x, the change in the run. So it goes from 0 to 20 and 0 to 10. So 20 divided by 10 would be
2x
2. Is it positive or negative?
is positive.
Yeah, because it's positive 20 divided by. Or this, I'm running uphill from left to right. Uphill, positive, right? So that particular slope for the f function, as we've pieced together with the g, is 2. Again, that slope is 20 divided by 10. Change in the rise divided by the change in the
And
run.
wouldn't the b be 20?
Where does the f function start in this piece?
Oh, 0.
Ah, right?
So you wouldn't write it.
Right? It's like a direct variation.
Okay.
If we're starting it there, that's where we're saying it started, for that particular piece.
And then the function for
That's where it crosses the y-axis. Right? Is it 0? So, that f function is, again, we're not here, we're not going to write plus 0, but b, as Jacob is saying, is indeed 0. Why? Because it crosses the y-axis, crosses the vertical axis at 0. You with me? Okay. Let's write a function now for the g function in a similar way. It's got to be mx plus b. It's got to be linear. But what is the slope?
You don't have
X
any.
plus 20.
Are we rising at all? Then what number did we use for not rising?
0, so you,
0.
Zero.
Did we run it all?
yes.
Do we run it all?
Yes.
Yeah. We go from 10 to 20, right? So how far did we run?
10.
10, but since we didn't rise, what's the number for nothing?
X, well, 0.
0. 0 divided by 10 is
Is 0.
0, right? So that 0 times x is the slope, hugs and kisses, for that particular part of the function.
you would-
But what is b?
20.
Isn't it
It
10?
starts at 20.
It starts, if we extend this on out, we can determine where it crosses that y-axis and where does it start? Or where does it cross the y-axis? Crosses at 20, right? So the b is going to be 20. Well, what's 0 plus 20?
20.
Right? So what I'm going to say, then this algebra for this piecewise function is those two functions. We'll leave the work up there to show how we did it. But this is the piecewise function of what we've graphed over there. Both the g function, which is y equal 20, or g of x equal 20, because it never rises, it's flat, okay? And the f function has a slope of 2. So,
Why didn't you put the X by the 20 when you moved it down? I didn't follow.
good question. Maybe somebody else has that too. If I multiply 20 times x, is that what we said we had here? Does this say to multiply 20 and x?
No.
No, this says multiply or add 20 to what?
0.
What's 0 times x?
Which is 0. Oh, okay.
So it disappears, right? That's a great question. That'll clear up a lot of misconceptions there that somebody else might have. Okay, great question. So again, that line that's flat like this, like the top of a table, right, it has no slope, right? Or it has a slope, but the slope is
0.
0. Okay? If I'm running on it, then I kind of like that. Until I stepped on a rock like I did this weekend. That's why you see me limping.
Oh,
I had my toe shoes on and stepped on a rock.
did you stub your
I've
toe?
got a heel bruise, no, it's pretty bad. So that's the function. That is the two pieces of functions that we put together to make this picture. Could we add more pieces?
Yes.
We absolutely could. And that way we can say, this is actually going to model our moving mean. Picture this with me, if you will. If this is modeling somebody moving, the f function, if somebody is moving, modeled by this algebra, the f, and that part of the graph, can you tell me something in English about that person moving? Can you look at this, or look at this, and describe to me that person moving?
We're running up the side of the mesa.
Moving, right? Running. Now, is he running up a hill? Not necessarily. Again, if this is modeling if the x-axis is modeling a distance,
And then
sorry,
modeling
a time,
Yeah.
and this is modeling a distance, the f function or the y-axis, the vertical axis. So this is distance and this is time. What is this modeling? Moving, or the speed,
Yeah.
right? How fast you're moving. So how fast is this person moving then at
You
this particular
accelerated
time?
and then stopped at a,
How fast is he moving? Constant?
Yes.
no.
Straight line. Constant speed. Straight line. Constant speed. Speed's not changing, right? We just cut the line off. You could extend it on out, right? Right?
Yes.
But that person is moving at a constant speed. What speed is that person moving?
He's moving.
Can you tell me the number?
10.
No.
Say it out loud, Kelsey.
10?
2. 2. Slope is rate of change. If this is modeling moving me, then the steepness of that line, the slope of the line is communicating to you how fast the person is moving. How fast time, how fast distance is changing in the time, divided by the time. Miles divided by hours. Feet divided by seconds. Miles per hour. Speed is the same thing as slope. Okay? So when you see the algebra modeling something moving, a car, somebody walking, somebody running, if they're running at a constant speed, then that line's going to be straight. And then the slope is modeling the speed. Okay, well, are you agree with that? Are you good with that? Okay? What about this person? This is a different person. This is the G person that we pieced together that. Or it's the same person moving differently. Still constant, isn't it? Still a straight line. But how fast is the person
Same
moving?
speed.
It's like not,
What?
Same speed.
Same. What is that speed?
It's
20.
Is it?
Yes.
oh, he moved 20.
Is this 20 times x?
No, it's not.
Is 20 the slope?
Oh no.
Oh no. What is the speed of that person?
0.
Why are you saying that?
Because he has no slope.
Has slope, but the slope is
0.
0. That means that the person is moving how?
He's not moving.
Not moving at all. What's that person doing?
Standing.
Standing still.
You better hope at least.
For how long?
20 seconds.
20 seconds.
Or
20 seconds.
10 seconds.
20 time units. That person is standing still. How long was this person moving at 2?
10 seconds.
10 seconds is how long that person was moving. And then so that person was moving at a constant speed of what speed?
2.
2 for how long?
10 seconds.
And then in 10 seconds, what happened?
He stopped.
Oh, he stops. And he stops for how long?
10 seconds.
10.
That's what you need to start understanding how the algebra of linear functions can model that car moving down that street. Okay? Car moved at 2 units and then hit a red light, saw a red light, and then he did what?
Stop.
For how long?
Uh,
However long he stopped at that red light is how long this line would be. But his speed would be
0.
0. But where would he be stopped at? Whatever height, however far he made it from home. Whatever the distance is from where he started at home to where that red light was. With me? Okay, so let's look at this. Moving mean. I'm going to have you practice this a little bit. There's another piece. We'll call it the H function. Talk to me about that person moving.
He's slowing down.
Is he slowing down? So it's not a straight line.
It is a straight.
It's a straight line, so what's his movement?
Constant.
It's constant. It's not slowing down. He's going at exactly the same speed all through this time. He's going constant speed. But let's talk to me about that constant speed.
Is he going in a different direction?
He is going in a different direction. What direction is he going?
Back.
Back where?
Back to the start.
To the,
Back to home. Right?
this is so
He has turned around and gone back home. Because this is what kind of slope?
negative.
Negative slope. So the distance went from 20 to what?
10.
He got closer to where?
To where he
Where he started. He went from 20 distance to 10 distance. So, but talk to me about the speed. How fast is it going?
Negative. Oh, rise over what? 20.
What?
Yeah, this is a little harder. So let me help you. Can you give me the coordinate
20, 20.
of where he started moving at the stop, at the red line?
20.
20 is the time, 20 is the distance. Can you give me this coordinate?
10, 30.
10 is the,
No. 30 is the x.
30 is the time,
10 is the distance.
10 is the distance. Can you calculate the slope now? And when you calculate the slope, you're calculating the what?
The change,
Of moving mean. What are you calculating of moving mean? Say the S word.
Slope.
The speed. Or the slope. But of the moving mean, you're calculating the speed Brandon's moving
10.
when you calculate the slope. 10?
mm,
Or
no, it would be,
20 minus 10. You always go to rise first, right? 20 minus 10.
So it'd be 1.
And 20 minus a third. Gotta go the same direction.
why are we taking those and then adding, or subtracting? What does that do for us?
Calculates the slope, like we learned back in Algebra 1 when we were babies. Slope. Rise divided by the run. 20 minus 10.
That would be negative.
How far have we changed here? We've gone from 20 to where?
30.
Oh, the slope's negative.
20 to 10, right?
Slope's negative.
That's the down. That's the rise change. But it's negative because we went down, right?
So the slope's negative 1.
How's the run change?
10.
10 again, right? So what's the slope?
Negative 1.
So for the h function, we have a negative 1 times x. We're not hillbillies. We don't write the 1. And we know it's negative 10 divided by 10. Should it be a negative slope? Ladies and gentlemen, what I'm sharing with you today is a mind-warping thing. It's a mind-warping thing. You doing whatever, Brandon, you're doing, or Cheyenne on the computer, one more day, you're robbing yourself of changing radically. You're going to stay right where you are, never having an opportunity to change. What is the b? Figured out the slope times x. What is the b of the h function? Where would it cross the what? Y-axis. Now this is a more difficult thing, but if we were doing this very accurately on graph paper, and I extended that line on up, whatever that number is what we would write for what?
For B.
For b. So, we don't know what that b is. Now we practiced this before we took our final in the fall. We practiced this. This was on the final. Let's review it. How would I find the b for that particular function? I'm going to write y here just for a minute to help you out because y is the same as h of x. How would I find what that b is? You remember what you reviewed for your final today? How would I find a number for b? How could I solve for b?
You'd have to put in a number for
Oh,
X.
Sarah's remembering some things. If I just had, I have 3 letters here, right? If I just had 1 letter, it'd be simple, almost insultingly simple to solve for b. So what numbers could I write for x and y for this h function? What numbers could I write for x and y? What number could I write for an x? And what number could I write for a y that models this h piece of function?
Any of the points on the line.
On that line, do you have a couple of points on that line sitting in front of you?
20 and 20.
20 and 20. Right there. That's a point on the h function, on the h line, 20, 20. So what number can I write for a y? 20. What number can I write for x? 20. Could you easily now solve for b? What are you going to do then, negative 20?
Move it over.
Move it to the left, it becomes?
Positive.
And you add it to its like term?
So it's
What is b?
B is 40.
40. Does that make graphic sense, even though we're not even on graph paper, that this is 40?
when I first wrote it, it was 35.
Does it make sense?
Yeah.
Okay? So what's the function for that h function? What am I writing for b?
40.
40. So now we've increased our piecewise function, adding 3 functions that we've pieced together. I'm leaving the work there for you to see in the video, and for you to capture in your notes. Piecewise functions. We're going to model us walking outside Thursday. Bring your jacket in case it's cool. Right? So we're going to start in place. We're all going to start on a starting line. we're going to move away from the starting line. We'll move away from it. What's your slope going to be? Positive or negative? Positive. If we stop, what's your slope?
0.
0. If I ask you to turn around and walk back to the starting line, your slope is 0, right? Or slope is negative, right? However fast you move, if you move really, really fast, faster than anybody else, how's that going to affect your line? Steeper. If you move really, really slow,
It's going to be
less steep. If you stop completely,
It's going to be
you're going to be flat. Feeling me on this? Man, I took you guys to a great place. I've never done that way before. So if you didn't capture it, if it didn't warp your mind in a good way this morning, you missed an opportunity.
It's a little hard to think.
It is hard to think about. So if you weren't thinking about it, if you weren't paying attention, you missed an opportunity for a really powerful mind warping. So what I'm going to ask you to do is on the web page, on the agenda, it asks you to go to page 131 and look at problems 1 through 7. Okay? One thing I want to add to this algebra real quick is I want to add where the domain is, because they actually do that pretty well for you in the book. So again, the domain here for this the G function. What do we write for the domain? It went from 0 to 10. Back. I want to make sure we understood that. I'm sorry, that was the F function. From 0 to 10. And the G function went from where?
Went from
10 to 20, didn't it?
Yes.
And then what about the H function? Where did that domain go? Since we stopped it here, we're starting it there and stopping it there. What's the domain there for the H function? It went from right? So that piece went from 0 to 10. This piece went from 10 to 20. This piece went from 20 to 30. Ladies and gentlemen, that's called piecewise function. The activity that we're going to go collect our raw data about your individual movement all together, all at the same time. Nobody's going to be watching anybody. We're all going to be doing it at the same time. Done this many years. It's called moving mean. And we're going to do that the next time I come back. Questions? We are the Ask Academy.